Cool. Okay. Um, yeah, I was discussing this paper we had recently with Justin Thaler on optimizing Sumcheck prover, and we thought maybe it's a good idea to just try and present it, get people interested. Um, so I'm going to talk about a simple new algorithm that we devised for optimizing the Sumcheck prover. Um, the basic idea is essentially coming up with a like an efficient way to multiply two simple numbers, and we'll see how powerful it is to get your optimization at a very low level, how powerful or useful it is when you look at the protocol as a whole. um, the paper is not named by this. What I'm going to talk about is some of the how the technique works, how the algorithm works, and how and what sort of encouraging results we see with some check prover. And we typically see for particular configuration we see a 12 or 13 times faster prover, faster sum check prover as compared to the naive algorithm. This is joint work with one of my colleague Yuval and Justin Thaler from E16Z. So let's get started. So before we actually discuss the techniques, I'll quickly go over a bit of basics of binary fields, which I'm sure you guys already know because I heard that these things have already been discussed in this hacker house. Um, so essentially what binary fields mean is the fields of characteristic 2. Um, it's the simplest possible definition, and by characteristic 2 we mean that if you add a number in the field to itself, it will give you 0. So 2 times p is equal to 0, where p is your field element. That's the simplest definition. Um, when we look at the simplest possible form of a binary field, it's just 2 bits, 1 bit number, which is 0 and 1. And that's typically called GF2. GF stands for Galois field. And when you have 0 and 1, this is indeed a field because you can define addition and multiplication, and then you can verify the properties that are required for a field that hold true. So because it's just bits, and that's what all of our chips that we use in our computers, laptops, phones, servers, whatever, all of them are based on these basic operations. Bitwise XOR and multiplication is just bitwise AND. When we try and go a level higher, let's say we want to understand what is GF4 or what is GF2 to the power 2. The way we construct this is using something called as extension fields. So if we take a degree 2 extension of your basic field, so basic GF2 contains 0 and 1, and now we want to take a degree 2 extension of it, that will give us GF4. Now in very simple terms, the extension field, to construct like an extension field, you can think of it like you are picking 2 elements from your base field to construct 1 element of your the degree 2 extension. Let's say it's a degree k extension, then you just take k elements from the base field and compile it together. That becomes your 1 element of the degree k extension field. So we'll stick to the binary fields case. So we'll see how we define GF4. So to define like these extension fields, we not just need a degree of extension, but we also need another parameter called as irreducible polynomial. I'll not go into the details of why we need these and all the math that works out for extension fields. But basically the idea of an irreducible polynomial is, if you define a polynomial over your base field and you divide it by the irreducible polynomial, your remainder is what you will get in the degree to extension in this case. Now, how do I determine why does this give us a degree to extension? The basic reason is it will depend on the degree of your irreducible polynomial. Very in very simple terms, if your irreducible polynomial is degree k, then you're going to end up with a degree k extension. We'll try to look at a quick example of what happens when we try to define a polynomial over our base field and then divide it by the irreducible polynomial. So let's take this example. Now this polynomial is indeed in the base field, and the reason for that is all of the coefficients of this polynomial are from your base field. So you can see all of the coefficients are 0, 1. So coefficient of x to the power 4 is 1, x to the power 3 is 1, x to the power 2 coefficient is 0, and then again 1 and 1. So this is indeed a polynomial over your base field. Now can somebody work out what would be the remainder of this polynomial when you divide it by the irreducible polynomial? Do you want us to work out very quickly? Yeah, so remainder is 0. So we can do something like this. And now I'll just, so addition and subtraction in binary fields is same. So I add in an x square, and then if I added it once more, it just becomes 0, because as I said, 2 times p must be 0. So let's see what's the remaining term. Now you see this becomes your irreducible polynomial, plus this also becomes your irreducible polynomial. And now if you divide this by m of x, you're going to get 0. So what this 0 means is, it's actually like if you actually solve this, it will be 0x plus 0. So the remainder of any polynomial you define over your base field, the remainder is always going to be one of these 4 values: 0, 0, 0, 1, 1, 0, and 1, 1. Does that make sense? So basically you see these 4 elements is what is nothing but your GF4. It's the degree to extension, or the elements in GF4 is basically these 4 elements that we see here. And now if we go back to what we said earlier, you can see these are pairs of zeros and ones. So you took your base field, and if you take all possible pairs, you get your next degree to extension. Any questions in this example? Okay. Okay, now we can do something more interesting, which is if we keep doing these degree 2 extensions um, over over our uh, over the new fields that we get. For example, if we start with binary field 0 1, we take its degree 2 extension. Now we take this as the base field, take another degree 2 extension. So we'll keep getting like larger fields. So you can imagine uh, you start with just 2 elements in your field, in your base field, and then after doing 7 or 8 steps, you'll reach a very large field. Um, and this is basically called as the tower of binary fields, uh, because you build the next field, keeping your previous field as the base field. Um, the, yeah.
So I wanted to ask, like, why only like degree 2 extensions? Because any 2 to the k is like a field.
Yes, you can basically, so it's not necessary. You can go from this directly to this if you define your irreducible polynomial of that degree. In this case, we are interested in leveraging the structure, like going step by step, because you will very soon see there is a nice structure that we get if we do this incremental thing. And even if we do this incremental thing, so let's say our objective, so doing extension fields, the objective is to create a larger field from a smaller field, right? Now from this small field you can derive like a 2 to the power 128 extension field directly. You can do that directly as well, but then even if you do these steps, it's only going to take 7 or 8 steps. So it's a definition that we are sticking with. We say that we'll stick with this degree 2 extension, and we'll see if that structure gives us some advantage in computation, and we'll see what advantage we have. Um, so we already seen 2 of these fields. GF2 is just 0 1, then GF2 to the power 2 is of course 4 elements, where X is called as either variable or indeterminate, whatever you like. Similarly, you can define elements from the degree 2 extension of your GF4. So this will contain 16 elements, and now you have 2 indeterminants, Y and X. So the indeterminants or variables are not really important. What's important here is you can see the elements are basically, in this you have 2 elements from the binary field. This is a 2-bit number. This becomes a 4-bit number. GF2 to the power 8 will become a 16-bit number, and this will carry on. So if you take like 7 degrees, if you take a tower of height 7 or 8, you will get like a 128 bit number. So what's the advantage of this structure? As I said, is let's say you take an element from GF2 to the power 8. Of course, this element, so I have not written the indeterminants because you'll have X, Y, Z, and then you keep carrying on. But I have just represented the bits, the binary numbers. Now the interesting thing with this kind of structure is an element in GF2 to the power 8, you can map it to element from GF2 to the power 4 from the previous field. Because effectively, if you have a binary number, 8-bit number, you can just split the most significant 4 and least significant 4, and you get 2 elements. Those 2 elements are nothing but some elements from the previous field. And again, you can do the same thing in the GF2 to the power 4, and you can map it back to 2 elements from your previous field. And you can keep doing this recursive thing until you realize that everything just boils down to your base field. So everything is just 0 ones. You can keep splitting these numbers. You can make a 128-bit number into two 64-bit numbers, and two 64-bit numbers into four 32-bit numbers, and keep doing that. Um, and this structure, this recursive structure that we are seeing, is the advantage that I was talking about. Why is this an advantage? Because the computation that we are interested is addition and multiplication, and this makes addition very fast. Addition is basically just bitwise XOR. So if you want to do addition in 2 to the GF 2 to the power 8, you just take this number, second number, you take bitwise addition, bitwise XOR. That should give you the result of adding two field numbers. Now compare this. Just imagine, like, if you have two numbers in BN254 field, adding them is a lot more computationally intensive tasks. So therefore, doing addition in binary fields is almost like it's almost free. There is no cost associated with it. What about multiplication? So for multiplication as well, we can leverage this recursive structure that we just saw, that element from a larger field, break it down, bring it down to smaller fields. And therefore, what you'll get, multiplication is slightly complicated, because to multiply two numbers A and B, you split it into two parts, each of them. The higher part and the lower part, H and L, both of them. Now you see, you effectively have to multiply these two polynomials in X. So multiplication now boils down to multiplication of polynomials. Can somebody tell me, like, let's say it costs 1 unit to multiply one higher or lower number with the other higher or lower number. Can somebody tell me what's the total cost of multiplying A and B in that case? Assume that AH times BH takes 1 unit, or any combination AL times BH, whatever, takes 1 unit. Okay, 4 is the naive answer, right? If you just like expand everything, you should do 4 multiplications. Can somebody come up with a slightly more efficient? Exactly. Karatsuba multiplication, you can do this in 3 multiplications. I'll quickly show, because it's actually very important to our discussion. Let's just call this as A0, A1, B0. And we'll do the naive thing first. So this is the part that we want to sort of simplify. So this is nothing but A0 plus A1, B0 plus B1, sorry, minus this remains same, this remains same. And then these terms basically you'll need to take out. So the first term, like multiplicand of A0, B0, will be 1 minus x plus the multiplicand of A1, B1, x square minus x, and then there is a multiplicand of x. Does this make sense? So effectively, you are only doing 3 multiplications. 1, 2, and this one is 3. Because this is so addition does not affect the degree of the things that you are doing here. So this is again like a uh, simple, like you can think about it like a simple base field element. This is also a base field. So you spend 3 multiplications instead of 4 using the Karatsuba trick. Okay, so coming back to multiplication in these, by the way, anyone has questions in the Karatsuba trick? Okay.
So the A and B from the extension field and A0 and A1 from the base field.
A0 and A1 is from the field that is one step lower to your A and B. So assume that these are from degree 2 extensions, GF2 to the power, these are 2-bit numbers, then A0, A1 will be 1-bit numbers.
Okay, you can, and so finally the A0 and A1 maybe from the F2.
Yes, yes. And let's say you have larger fields, like let's say A and B are from 64-bit field. So then you'll have to keep breaking them into smaller pieces and keep doing this recursive Karatsuba algorithm. Keep doing this multiplication recursively. That's why I said multiplication is slightly complicated. It's not as straightforward as addition. But again, it is simple enough because you can write a recursive Karatsuba multiplication, and that should give you the multiplication of two field elements in any extension of your base field. Does that make sense before we go ahead? Okay. So the interesting thing is multiplication in extension fields is generally very expensive, because you can imagine you are trying to do a recursive algorithm. You break like 32 bits into 216 bits, each of the 216 bits into 8-bit numbers. And you keep doing that, and at every step you are doing some multiplications. You are doing some kind of Karatsuba algorithm. So this recursive Karatsuba algorithm results in a very expensive computation. So just to give you some ballpark of like what's the comparison, let's say we take the base field is, let's say, just 2 bits, GF2, and we take extension field GF 2 to the power 128. So elements in this field are 128-bit numbers, and elements in this field is just 1-bit number, right? So this is like a degree 128 extension of this. Yeah, degree of extension, exactly. Now, the last column, what I am measuring is the ratio of how much time it takes to multiply 2 elements in this field versus how much time it takes to multiply 2 elements in this. So 2 elements in this should be very fast, should be actually equal to your processor speed, because it's just doing simple AND operation. Multiplication in this, you need to do the recursive stuff. So it turns out it's almost 14,000 times slower to multiply 2 numbers as compared to 2 numbers in your base field. So this is basically just to highlight, it is very expensive to multiply 2 numbers in your extension field as compared to your base field. So even if you take like other like configurations, let's say I take this as my base field and this as my extension field. So this is like a degree 32 extension, because from 4 bits you are going to 128 bits. Even in that case, it's almost 50 times, this is 50 times slower than one multiplication in the base field. So the point I'm trying to highlight with this table is multiplication in extension fields is very expensive, especially for like snark use case, because in snarks, let's say we take Binius, we need extension field of degree 128, because for the security of our algorithm, we at least need to have GF2 to the power 128 as your extension field, and let's say your base field, for simplicity, you just take the binary GF2. So in that case, you see multiplying one extension field, E stands for one extension multiplied by one extension element. That's almost 14,000 times slower. So therefore, extension field multiplications are super expensive. And even if you do your own implementation of binary fields, you'll get something around this number, maybe 20,000, 30,000 as a factor of this multiplication. So the bottom line, extension field multiplications are very expensive. Okay, now, yeah.
So, so as you increase the extension of the base field,
Mm-hmm.
the ratio should become smaller and smaller, right?
Yes.
But why is it increasing and then decreasing?
No, it's not increasing. So the second number is, so it basically depends on the degree of extension. If the degree of extension is larger, then your ratio will become large, because you need to do, like, for this degree of extension, you need to do recursion, I think 7 times. 2 to the power 7 is 64, right? Sorry, 6 times. You need to do 6 times the recursion. In this, you need to do 7 times to, in multiplication, to do this Karatsuba recursion. And that's the reason you see, like, the decreasing trend in the factor of multiplication. Okay, why do we care about everything? Like, everything that we just discussed, the point was that extension field multiplications are very expensive. So why do we care? The reason we care is because there's a new snark called Binius that basically says we'll ditch all these fields, traditional fields like BN254 and like BLS and so on. We'll work with these binary fields because we see potential that addition and multiplication in those fields is much more efficient as compared to your traditional fields. So Binius is like a new snark that enables snarks or that gives techniques to develop snarks over binary tower fields. Now, specifically, Binius is a very fast commitment scheme. So any snark consists of 2 pieces. One is commitment scheme, one is your IOP. For example, Plonk uses KZG, like the original Plonk used KZG as the commitment scheme, and IOP it used a novel like technique where it shows certain relation between a bunch of polynomials, and then you divide those polynomials using a vanishing polynomial and so on. So I'll not go into that. But basically, a snark consists of 2 components, commitment scheme and IOP. In this case, in case of Binius, so Binius is a commitment scheme. It's very fast, very efficient, because in binary fields, as I said, multiplication and addition are much more efficient as compared to your traditional fields like BN254 or BLS, whatever. So your commitment scheme becomes very fast, and then the IOP that they use is Sumcheck. Now the problem that arises is this typical paradox that we see in accelerating any prover. If, let's say, a prover consists of like 10 parts, if you only accelerate 8 parts, it's not enough, right? Because the remaining 2 parts will become the new bottleneck. That's exactly what happened. The commitment scheme is so fast that Sumcheck becomes your new bottleneck. Because before this, nobody thought Sumcheck could become a bottleneck. Because it was linear time and everything is in the field, and nobody expected Sumcheck to become a bottleneck. But so this is a quick slide from Radhi's talk on Binius profiling, and I'll zoom in a bit. So in this, we can see the pink part is the proof time, the total prover profile. And you can see this batch proof is basically a sum check, or specifically it's a zero check. And you can see it's almost 70 to 80% of your total prover runtime. This yellow box is the sum check part, and the rest of it is the commitment scheme part. So therefore, sum check now becomes the new bottleneck. So you made this so much faster that now this becomes the second most dominant thing. This becomes, sum check becomes the dominant cost. Now, specifically with sum check, one last thing to note here is this is the first round of sum check. This is the second round. This is third round, fourth round, so on. Because sum check has these log n rounds. You can see first, second, third, fourth, first 3 or 4 rounds are very expensive. If we can specifically target to make them faster, even that could be good enough. Any questions? Okay. Okay, so now we have set up this paradigm where we are interested in making sum check faster. That's one thing that we discussed. And the second thing that we discussed is we need to do this specifically for binary tower fields. Can we, so we'll try to answer, can we actually make the prover faster? Now for that, we discuss product sum check, because in any proof systems, if you're using sum check as an IOP, just the vanilla sum check is not is actually a bit useless. What you need to you need a variant of sum check that works on products of polynomials. So let's say you have a polynomial relation like this, and you are using sum check to prove this relation. So if we quickly take a look at what the definition of a round polynomial in sum check is, I'm calling it as SI evaluated at C. C is some variable. Typically the value of C will be 0, 1, 2, up to, it's a small integer typically. So in the previous slide, I showed you that we are interested in making this round polynomial computation faster, right? Because that's the new bottleneck. The first 3-4 rounds, this was very slow. Like computing this round polynomial SI was very slow. So that's why we are looking into the definition of round polynomial. Now, in this particular case, because our sum check polynomial is a product of these bunch of polynomials, we just substitute the product, make the notation a bit clear. Now, the most critical part is this part. So R1, R2, Ri minus 1 are challenges from the previous sum check rounds. Now, this evaluation, let's look at only the jth polynomial. So the jth polynomial part is an extension field element. Do you agree? Because we are evaluating it at extension field elements. The challenges are extension field elements. So if you are evaluating a polynomial at extension field elements, let's say this, let's say you have a simple polynomial ax plus b. Now if you substitute this with r, and this r is a very large number from extension field, your result also is going to be in the extension field, right? So therefore, this box is product of extension field elements. And as I said, product of extension field elements is very expensive, right? And that is exactly why we are seeing this become the bottleneck. Because in every round polynomial computation, after the first round, you will have lots and lots of extension field multiplications, right? Which is very expensive. Can somebody tell me why this is not a problem in the first round of sum check? There's no challenge. In the very first round, there is no challenge. So that's why everything is still in the base field. Um, so basically, this product of extension field elements is what we want to solve. Now, if this was some random product of extension field elements, we would have no way to optimize this, right? Like you can't do anything. But then this has a very specific form. These polynomials are not some random polynomials. These are multilinear extension polynomials, in which, so this Pj can be defined in the following form, where it's a linear combination, but you can separate the challenge terms and you can separate the witness terms. Does that make sense? Do you agree with this statement? The polynomials that we deal with in Sumcheck, in specifically our snarks, are always going to be multilinear extensions. So they are of very specific form. And the form, I'm just simplifying that form here, that you'll have some challenge terms and some witness terms. It's a linear combination of that. So the hint I'm trying to give is, can we leverage this form to reduce extension field multiplications as much as possible? So by that, what I mean is, in this example, if A and B are from the base field, are smaller numbers, and if I'm substituting R, by substituting R, I'm making the whole thing large. So I'm saying, can I delay the substitution of R as much as possible, so that we can avoid extension field multiplications as much as possible, or minimize them as much as possible. That's exactly what we are trying to do here. These witness terms are from the smaller field, are from the base field. So these, in this case that we are discussing, GF2 and GF2 to the power 128, these are 1-bit elements. These are literally zeros and ones. But these, each of them is 128-bit number. So the idea is to separate your challenge and witness terms as much as possible, and to delay it as much as possible. So this is a quick example we are looking at. Let's say you have two polynomials, P and Q. Instead of looking at product of D polynomials, I'm saying let's only look at two polynomials, and let's look at the second round. Okay, so second round, you only have one challenge, R1, from the previous round. Now your P and Q can be written in this particular linear form. 1 minus R1 times whatever is your P evaluated at this 0. C and X you can ignore, it's the common term everywhere. So red term I'm showing as the 0 term, green term I'm showing as the 1 term. Now let's say I want to multiply these two polynomials. Can somebody tell me, these are small numbers and these are very large. Can somebody tell me how many multiplications will I need to multiply these two polynomials? I want to multiply these two. Each of them contains two terms. It's 4, right? Because if you just do a naive multiplication, you'll get 4 terms, all cross terms. Agree? Now, the main idea of our optimization is, instead of doing 4, can we do 3? Can we come up with a variant of Karatsuba trick to do 3? Right? So going down from 4 multiplications to 3 is pretty straightforward in this case. Do you agree? Now, it looks pretty simple that we should be able to apply the Karatsuba trick here. But now the challenging part is, can we extend that trick to further rounds? So this, I'm saying, is only 2 polynomials. First problem, we are only looking at 2 polynomials. Second problem, we are only looking at the first round. can we generalize this for further rounds? This Karatsuba trick, can we come up with a more general Karatsuba trick to apply it to more rounds? And can we also generalize to include multiple polynomials? Like if I have, let's say, 10 polynomials, and we answer positively to that. So we come up with a structure that is that you are able to use a Karatsuba generalization to this particular use case.
Correction. Where's the 1 minus R1 comes from?
This one?
Yeah.
So this is the definition of multilinear extensions. So if you quickly,
It just comes from Sumcheck challenge. The R1.
oh, R1 is the Sumcheck challenge, but you are asking where does this 1 minus R1 come from?
Yeah. Isn't that part is one R1 and another part is 1 minus?
Yes, exactly. So typically, I think I understand. So typically, you see linear polynomials of this form, right? So mx plus c, where m is slope and c is intercept, and so on. But then, in case of multilinear extensions, we have this particular form: this multiplied by something plus x multiplied by something. The reason for that is by multilinear extensions, by definition, it means this box is your evaluation at this point, and this box is your evaluation at 1. So evaluation at 0 and 1 is what? Okay, the other way to say is, let's say you have numbers, two numbers, 4 and 1. If you want to represent these two in form of a polynomial, there's tons of ways, right? You can draw one straight line that passes through both of them. You can also do higher degree extensions. What we are interested in this straight line that passes through both of them. And the simplest form to represent this is this. So if you substitute x equal to 0, this will go to 0, this term, right? And if you substitute 1, this will go to 0. So it's basically like encoding these two numbers, 4 and 1, in the simplest possible way in the linear case. So it's the definition of multilinear extensions. That's why we have this 1 minus R1 term. We go ahead. So what we are going to do next is we'll try to figure out how do you generalize this Karatsuba trick and reduce the number of multiplications. Because one thing that we realized is we can separate out the challenge terms and separate out the witness terms, just like I've shown here. And then if you have multiple polynomials like this, you can do the naive multiplication. It's called school book multiplication, right? Like if you have two such polynomials, let's say this one has 8 terms, second one has 8 terms. So if you multiply both of them by naive way, you'll get 64 terms, right? So one part you have figured out, which is we have separated out large numbers like extension field numbers. The second part is what we are focusing on now. So instead of 64 multiplications of these witness terms in this particular example, can we reduce it? Just like instead of 4 in this case, can we reduce it to 3?
So you sum the right side first.
Sorry?
You sum the right side first.
You cannot. You mean this side?
No, I mean under this here. You sum the PC and Q with D because they share the same coefficient. Can you do that?
So I don't understand. Can you repeat?
Because they share the same coefficient, so you can
Which ones share the same coefficient?
P0 CX times Q1 CX and P this one and this one.
Yeah, exactly. So that's exactly what Karatsuba trick is, which means in this case you can reduce these 4 multiplications in the base field to just 3 multiplications. That I agree. What I'm saying, can we do it in a more general case? And do we have benefits of that, or is it like does it make our prover faster? Um, so so I'll quickly like describe how do we generalize this, and that's basically the essence of this paper. And then the last part would be just quickly discussing a few benchmarks and see if we actually get like a 10x improvement. Uh, so I'm looking at a very simple example here. I'm only looking at linear polynomial. So 1 minus x times some alpha, some evaluation at 0, and x times some beta. Now if I want to multiply d of such polynomials um, using the naive multiplication, you can do that, right? So you'll have 2 to the power d terms here. These coefficient products and variable products, you can do the naive method, right? Like this is one linear polynomial and you're multiplying d of such linear polynomials. You can just like expand it entirely. Now what's the cost of this? So in this case we have separated out the variable products. We are only interested in measuring what's the coefficient product cost. So it's actually equal to d minus 1 times 2 to the power d, because in one term you need d minus 1 multiplications and you have 2 to the power d such terms. So that's how you get the number of bb multiplications. What do I mean by bb? Base field times base field, because remember all of these alpha beta are from the base field and only the challenges are from the extension field. Now effectively it boils down to, can you make this multiplication efficient in a more general case? So I'll ask a quick question, and if somebody answers that, then I don't even need to discuss this slide. Let's say you have 2 polynomials in coefficient form and I ask you to multiply those 2 polynomials. Forget about like binary fields, just 2 polynomials in any field. So what would be the method that you'll employ to multiply 2 polynomials in coefficient form? And the objective is to do it efficiently. Who said FFT? Yeah, exactly. If you have 2 polynomials, you can multiply them in coefficient form, but then it will lead to like lots of multiplications, right? Instead, you convert it to evaluation form, both of them, you take FFT, and then if you multiply, it's element-wise multiplication, it's much more efficient. So you apply the same method here. What you say is you have d polynomials that you are multiplying and you want to do it efficiently. So let's just convert all the d polynomials to their evaluation form and then multiply them. So we evaluate each point, each polynomial on d plus 1 points. Why d plus 1? Because the degree is d, right? You have linear polynomials, like this is linear, and then you are multiplying d such linear polynomials, so degree is d. So you take any d plus 1 points, just like in FFT, you need to, in entity, you can take any set of evaluations. For it to be efficient, you need it to be roots of unity. But in this case, there's no concept of roots of unity. So I just take any d points. I take the simplest possible, d plus 1 point, sorry. And we just compute point-wise multiplication, right? So I evaluate all these polynomials on d plus 1 points, and I can do that efficiently because in case of FFT, this evaluation matrix that we generally have in this form consists of all roots of unity, like omega, omega square, and so on. And that's what makes it like efficient to do FFTs. But in this case, it's even more simpler, because let's say I take E0 and E0 to ED as 0, 1, minus 1, 2, minus 2, and so on. Like I take very small integers. So what that would mean is computing these evaluations is much more faster. Like it's much easy, as long as your evaluation points are not large numbers. Now let's calculate what would be the total number of base field multiplications if we use this method. So assume that the evaluation part is free. Assume that we don't need any extra cost to do the evaluations of all these polynomials. Of course, there's a finite cost, but we can consider it to be negligible because these numbers E0, E1, ED all are very small. So if that is the case, then we just need d minus 1 times d plus 1 base field multiplications. And why is that? Because you have d plus 1 evaluation points, and on each evaluation point you want to compute this term, right? This term. So this term, computing like d products requires d minus 1 multiplications, and you have d plus 1 such evaluation points. So it's effectively just multiplication in the evaluation form. So this is a comparison. First method is called school book, or there's lots of names. It's the naive method. And the second method is called Tum-Cook method. Like it's based on a Tum-Cook idea, but we have basically extended the idea of Tum-Cook to a more general scenario. Now you see the dependence of this is exponential. In D, dependence of this is linear in terms of D. And that's what becomes the significant factor. Like if you do the naive way, you'll have a lot more base field multiplications. If you do the Tum-Cook way, you'll have a lot less base field multiplications. Another side effect of this is the memory required for the naive algorithm is this, because you need to store all possible terms, like all of these terms you need to store in this. So memory is also equal to this. In this, memory is also equal to this. So you need exponential memory. If you use the naive method, you need linear memory. Technically this is quadratic because there's also a d minus 1 term. So it creates a big gap between the amount of memory that you require in naive algorithm versus the efficient algorithm. And the very last part is, okay, how do we plug this into our Sumcheck, and how is this useful to us? So I'll not go into like, because it's pretty involved, like how do you actually plug this into like a more general form, but I'm just showing the simplified form here. So this is what our form boils down to, because effectively you are computing some multiplications here and then you are adding them up with some x terms. You see, like there's a bunch of x terms and that is being multiplied to some coefficient terms. So this is a general form that I'm representing this full thing in this simplified form. And this, we have a quick like comparison of what happens in the two algorithms, like school book and the Tum-Cook based algorithm. So the range of this sum is exponential in the school book, it's linear in the Tum-Cook. Rest of it let's not worry about that. So going back to Sumcheck, how do we plug this in? So we want to compute this product of d polynomials. So effectively we can just think of it as this form, like just substitute alpha j and beta j instead of these large polynomial expressions. So you want to compute this product, and as I showed in the previous slide, it's nothing but you can simplify it to this form: sum of some extension field terms, like these are like large numbers, multiplied by product of smaller numbers. And for this, we came up with two techniques. One is the naive algorithm, one is the efficient algorithm. So you can basically going from this step to this step is what I wanted to demonstrate here. Now we'll see like how this generalizes. So you start with the product of d polynomials, right? Then so this blue part, this is nothing but you can simplify it as, so ignore the bottom part. This is something that you can write as a sum, and then inside you have the product. So you separate your challenge terms. I should have had R1 here, sorry about that. So you separate the challenge terms, you separate the coefficient terms. Now you still have more challenges left here. So now only look at this part. You can again split it into challenge terms and coefficient terms, this pink part. If you have more challenges left, you keep doing that. And that's exactly exactly how you plug this technique in your Sumcheck. So in the third round, let's say this is third round, if you had only 3 challenges, you'll do 3 iterations of this. So you'll have 3 sums like K1, K2, K3. I should have had this K3. And that's how you basically plug your technique. So the bottom line or summary is you separate the challenge terms, you do that step by step, and for handling the coefficient part, you have come up with a more efficient multiplication technique. We have the implementation of 4 algorithms, the naive multiplications. So first of all, we have the very naive Sumcheck algorithm over binary tower fields. Second algorithm is like a more space efficient algorithm from 2011 paper from Justin Thaler. The 3 and 4 is what we are interested in the sense that algorithm 3 actually contains the technique that we discussed, the school book multiplication. Algorithm 4 contains the Tumcook based efficient multiplication. So we have the code open source. We would definitely love if you could like take a look. There are a bunch of to-dos in the code that if you're interested, this is in Rust by the way, and leave a star if you like the code. Yeah, so the last thing that I don't have in the slides is I'll just quickly show how we run a bunch of tests and just compare some timings of how much improvement we can see in the end-to-end prover. So, right, okay. Can you guys see my screen? Okay. So I'll quickly explain like the structure of the repository. So in algorithms, you have 1, 2, 3, and 4. So as I just explained, these are the 4 algorithms where we implement the end-to-end Sumcheck prover. We also have the binary tower field implementation, which contains basic like addition, multiplication, inversion operations. So we implemented our own binary tower field as a backend that the Sumcheck would use. There's bunch of tests, there's bunch of benchmarks. In the tests, we'll try to run this test just to demonstrate like what's how we can like compare the end-to-end runtimes. So what I've done here is we define a particular degree, we define a particular threshold, and by threshold, what we mean is this optimization that we are using is very memory intensive. Like you need a lot of memory to do all the separation of challenge and witness terms. So you can't use it for all rounds of Sumcheck, otherwise you'll need a lot of memory. So the good thing with this, with our algorithms, is we can use those algorithms only for first few rounds. Let's say only first 3 rounds, and then for rest of them we switch back to the naive algorithm. And the reason for that is exactly in the profile, Binias profile that we had. Yeah. So you see, first round, second round, third round, fourth round, the first few rounds is what is the most critical part. So what we do in the code, we implement it in such a way that you can only use our algorithms for first few rounds and then switch back to the naive algorithm. So threshold here means after what round you want to switch to naive algorithm. So you have degree. So degree, typically, like if we talk about let's say Jolt or any like Spartan or any proof system, the degree that's relevant is 3 to 6. So either it's a multiplication of 3 polynomials over which you want to run Sumcheck, or 4, 5, 6. So you can set the degree and then you can just, so what this runs, first it runs the naive algorithm with different like instance sizes. So 2 to the power 10, 2 power 12, 2 power up to 2 power 16. You can increase this to see what happens later. Then we run algorithm 3 and then we run algorithm 4. So what we are interested basically is in how much improvement algorithm 3 and 4 gives us, because in 3 and 4 we separate the challenge terms and separate the witness terms. So we minimize the number of extension field multiplications. That should itself give us a big boost in our prover time. And then on top of that, if memory is also constrained, let's say we want to implement this on GPU or limited memory devices, then algorithm 4 is what is the best, because it requires linear memory instead of exponential memory. So I'll run this test and then we'll sort of wait until it runs. I have some test results that I ran before the talk. So until this runs, we can quickly take a look at some previous configurations that I ran. So let's say I take degree 2 Sumcheck and I take threshold equal to 4. So after the 4th round, by the way, is this visible? Should I make it bigger? Okay. So these are like the run times. So let's say if I want to compare for n equal to 16, instance size equal to 16, the naive algorithm takes like 70 seconds, right? And if we look at pre-computation is like the algorithm 3, Tumcook is algorithm 4. So this takes 12.95 seconds and Tumcook takes 12.7 seconds. So algorithm 3 and 4, purely from a runtime point of view, 4 is very slightly better than 3. And I'll describe why is that the case. So what we are seeing here is we are not seeing a big boost because of using this Tumcook or like fancy Karatsuba, generalized Karatsuba technique, we are seeing a very minor boost, but I'll describe when it can become a big boost. So if you compare, this is like 12 seconds and this is like 68 seconds, so it's like a 5.5 times improvement over the naive brewer. So if you have this configuration, you see a 5x improvement, which is still a big deal because, as I said, Sumcheck was becoming the bottleneck, and if you make the Sumcheck part 5 times faster, again commitment scheme might become bottleneck. So you'll have to keep like figuring out what's the best configuration. Now I promised 10x, so I was a bit nervous. Will we get 10x in one of those configurations? So I tried a bit more like configurations. Let's see if we take degree 2 and threshold equal to 5. So prover time for naive 72 and prover time for this is like 8.6 seconds. So this is like 9 times. Yeah, so 9 times. And if we like keep going, you see this. So if the threshold changes, naive algorithm is not affected, right? Because this threshold idea only applies to algorithm 3 and 4. So if we look at like, so we'll just like remember this naive algorithm runtime. Let's say it's 70 seconds. So it was 68 and 72. Let's take 70. Now, if we increase the threshold, we see an improvement in the runtime of your algorithm 3 and 4. So 7 seconds versus 70 seconds. So here you start seeing the 10x improvement. But if you go beyond the point, let's say you take threshold 8, now your 3 and 4 again increases. So it's like this parabolic structure where you'll peak at certain configuration and then again you'll lose the benefits. The reason is if you do it for more rounds, the amount of computation that you do increases, because of course it increases because in every round you need to do this separating challenge and witness, and then the challenge terms you need to do all these evaluations, and as the number of rounds increase, the sizes of these increases, because in round 8 you'll have 7 challenges, so you'll have 2 to the power 7, like 128 terms in one polynomial, that being multiplied to and 3 such polynomials being multiplied. So basically this is so this will not keep increasing the performance, will peak at like 6 or 7. Let's look at 7. Yeah, it peaked at like 6, so 6.59, 71 seconds divided by 6.59, you get 11x improvement. And similarly, if you look at d equal to 3, you can again like run it in different configurations to figure out like what's the peak, what's the configuration where it peaks. If we want to quickly check, let's say d equal to 3 and t equal to 3, naive algorithm takes like 110 seconds. This is on my laptop, by the way, so it's pretty slow. My laptop is like 4 or 5 years old. I'm sure it would be much faster elsewhere. And algorithm 3 takes 36, so it's like a 3x improvement as compared to the naive algorithm. Threshold equal to 2. Okay, so yeah, it should, for degree 3 it should peak somewhere around t equal to 4 or 5. It peaked for degree 2 at t equal to 6. For degree 3 it would be somewhere before that, and you can keep doing this. It's still running. Anyways, so that's the summary. Basically, you can get a 10x faster Sumcheck right away if you are working in binary tower fields. The very last takeaway from all of this is our techniques apply to Sumcheck more generally. Like, it doesn't need to be just binary tower fields or extension fields, it applies more generally. What do I mean by that is, What we tried to do is effectively, if you have these two paradigms where you have some small numbers, your witness is small number and your challenge is a big number, then our techniques will still apply. For example, if you look at any ZKVM or Plonk prover or any prover, witness sizes are typically small. You can consider witnesses to be, let's say, only 32-bit elements. But the challenges are large. If we take BN254, the challenge is probably going to be like a 250-bit number, right? So as long as you have this parity between your witness size and your um, challenge size, which is actually the case for all practical proof systems that we are using, your witnesses are generally very small, like most of them are 0 ones, then you can still apply our techniques. Now you won't get a 10x improvement. Let's say if you use our algorithms in BN254, we actually have the implementation as well that works for BN254. It's on a different branch. I'll share that in the slides. You get like a 3 to 4x improvement. Let's say if you're speeding up Sumcheck over BN254, which is still pretty good because if you're accelerating Sumcheck by 3 to 4x without any like hardware, without anything, it's still pretty good. So I think that's all for today. Any questions?
So in your example, you take the product Sumcheck.
Yes, product Sumcheck.
So does this method apply all the Sumcheck?
Yes, it does apply to all Sumchecks.
Okay.
Like,
But you use this product Sumcheck is because this is the most cost.
so this is a product Sumcheck. Let's say you have three polynomials, P times Q times R. Whatever I described applies for this case, but then in practical scenarios, you'll have something like A, B, C minus D plus P times Q, all this multiplied by some E polynomial. So you'll have something like this in your, let's say, Jolt prover or Spartan or whatever. So our techniques apply in this case as well, because effectively this is this like the largest product will determine what your running time is, because the largest product is the most dominant one. But if you have like additions of products, our techniques will still apply. Yeah, what other technique or what other cases? You might have like p square of x times q of x, these cases, but this is again also a product of degree 3. So our techniques apply to like more general form of Sumchecks. Okay, questions, comments?
Does this work for parallelized?
Does this
Can you-
work
can you
for?
make it parallel?
Yes, we are working on a GPU implementation of these algorithms because
I run the test, it was quite slow.
yeah, these tests.
Yeah, everything is.
Yeah, it's very slow because this is a proof of concept implementation, mainly to supplement with our paper. So this is not at all optimized if we think about parallelism. Like we have some basic parallelism used in the Rust implementation, but it's not optimized.
That's probably I see only one core.
Yes, exactly. So we have not even thought about leveraging parallelism for this proof of concept. So I think it did run. Naive algorithm takes 216 seconds, and then so the improvement here is like 2x or less than 2x. Cool. Okay. So I think, yeah. Question.
So for the pre-computation method, it's yes, you said it was more memory intensive.
Yes.
You deconstructed it
Yes. Yes. I'll actually show you a plot. Is our paper? There's a plot in the paper that we do for memory, if I remember correctly. Yeah. So this is a theoretical plot of what's the memory requirement of algorithm 3 versus 4. So you see, in different configurations it's going to vary, but if you take let's say d equal to 3, degree 3, which is the most prominent use case in like modern proof systems, and let's say you take 17, like 2 to the power 17 as your instance size. So you see like a 5x uh, like a 5x difference between the memory requirement of algorithm 3 versus algorithm 4. So algorithm 4 makes a difference. The key selling point of algorithm 4 is the running time of algorithm 4 is always going to be less than algorithm 3. It will be very slightly less. In some cases it might be a bit more, but the running time is not the key selling point. Memory is the key selling point, because if you implement this in GPU or any memory constrained device, this difference is what makes kills algorithm 3, but it will make it possible to run algorithm 4. I'll show you some quick numbers. Yeah, so if we take uh, instance size 10, 2 to the power 10, algorithm 4 requires 4 MB, but algorithm 3 requires 4.2 GB. So even at p equal to 10, algorithm 3 becomes unusable, because 4.2 GB is something that can't even fit on like basic computer, basic PCs. Um, Yeah, and number of multiplications, BB multiplications, there's also a very big gap. Algorithm 4 is way better than algorithm 3, but then number of BB multiplications is already the least dominant part. The extension field multiplications dominates everything, especially in binary fields. But in case of BN254, let's say we do this in implement our or benchmark our techniques on BN254 Sumcheck, then you'll see a big gap between running times of algorithm 3 and 4 as well, because in that case the base field multiplications, like witness multiplications, let's say you multiply 32-bit number with a 32-bit number in a BN254 field, that's much more expensive than multiplying two 32-bit numbers in binary fields, because in binary fields it's much more efficient. So if your BB multiplications also become expensive, then you will see a gap between algorithm 3 and 4. More questions? No? Cool. Okay. I think that's all I had.